Good morning, everyone, and welcome to Friday of WWDC. Thank you. My name is Eric Turnquist, and today Brad and I are going to talk about working with heif and hevc. So first off, what is hevc? hevc stands for High Efficiency Video Coding, and it is the industry standard next-generation video encoding technology. It's the successor to H.264. Now, for the more important question is why? Why is Apple going through all of the effort to deliver a new codec? H.264 has been really good to us for over 10 years. Now, we thought about this a lot, and we really want to enable new features, and unfortunately, H.264 has reached the limits of its capabilities. We want to enable new features like 4K and larger frame sizes, higher bit depths like 10-bit, and wider color spaces like Rec 2020. Now, we want to do all this while lowering the bitrate, not raising that. So how do we do that? Well, we do that with hevc. So now, how much lower are the bit rates we're actually seeing? Well, for generally encoded content, we're seeing up to a 40% bitrate reduction for H.264. So this is a really big deal. And for camera capture, we're seeing up to a 2 times better compression compared to H.264 and JPEG. So another really big deal here. And we're making all of these changes today. So if you've installed the iOS 11 seeds, we've enabled hevc movie and heif image capture by default. So that means many of you have already captured heif images or hevc movies without even knowing it, and it just works on our platforms. Let's go over what we're going to talk about today. I'm going to cover the hevc movie side of things, and Brad's going to cover the heif image side of things. We're going to cover accessing this content, playing it back and displaying it, capturing it, and creating heif and hevc movies, and then export and transcode. So first, let's cover access. So many of you are using PhotoKit, and PhotoKit will deliver hevc assets for playback. So if you're using request player item or request live photo, they will give you automatic playback without adopting any new APIs. So this should just work. PhotoKit can also deliver you hevc assets. So if you're calling it request export session, it will transcode to the existing preset you're already using. So if you're using one of the dimension presets that used to give you H.264, it will still do that. And we'll cover new presets we've added for hevc. If you're calling request AV asset, it will give you access to the hevc media file, and this will have an hevc video track inside of it. Now, if you're a backup application, you want access to the raw bits. So you're probably calling it request data. So I want to make note that this will actually contain the hevc video track inside the movie file that you receive. So you need to be able to handle this. Now that you have this content, let's talk about playback and display. HEVC playback is supported in our modern media frameworks like AV-Kit, AV Foundation, and Video Toolbox. We support HTTP live streaming, play while download, and local file playback. And we support MPEG-4 and QuickTime file formats as the source. And here, there's no API opt-in required. Things should just work. We support decode on Mac OS and iOS. And now let's go over where we have hardware decode support. So we have 8 and 10-bit decoders on our A9 chip, so that's the iPhone 6s. And we have 8-bit hardware decode on our 6th generation Intel cores, that's Skylake, and that's the MacBook Pro with Touch Bar. We also have 10-bit decode on the 7th generation Intel Core processors, and that's Kaby Lake, and that's the brand new MacBook Pro with Touch Bar. We also have 8 and 10-bit software decode fallbacks on macOS and iOS. So now let's go over some code you might have, and let's convert it to hevc playback. So here we're playing My Awesome Movie, making a URL, then a player, and playing it. So this is the H.264 version. And now here's the hevc version. There's no changes. So to play an hevc movie file, you don't need to change any of your code. We want to have you think about a couple things. So the first is about decode capability. And if you're asking the question, is there a decoder on the system that can handle this content, this API is for you. This is useful for non-real-time operations like sharing or image generation, and it can be limited by hardware support. So not all of our hardware decoders support every frame size. Now, for the more important question is about playback capability. If you're asking, how do I have the best playback experience for my customer, this API is for you. And many of you are probably already using this API. So not all content can be played back in real time, and we have different capabilities on different devices. So if you want to have a one-stop shop for the best user experience for playback, whether that's 1x or 2x playback, rewind, scrubbing, or fast forward, this is the API for you. Now let's go on to hardware decode availability. If you want to get the best battery life during playback, you want to play back on systems that have hardware decode support. This will also get you the best decode performance. So we have new Video Toolbox API that you can query. Is there a hardware decoder supported for this codec? Here I'm showing you hevc, but you can also use it for any other codec. Now for the final question for playback. Which codec do I use for playback? Do I choose H.264 or hevc? Well, if you're concerned about delivering the most compatible content or want to deliver one asset that just works everywhere, choose H.264. Our platforms have supported this format for over 10 years, and there's broad adoption in the third-party ecosystem. However, if you want the smallest file size and latest and greatest encoding technology like 10-bit, choose hevc. You'll have to decide what works in your application. And with that, let's move on to capture. So capturing hevc is supported with AV Foundation, and we support MPEG-4 and QuickTime file formats as the destination. We support HEVC capture on our A10 chip, so that's iPhone 7. And now let's go over the capture graph that many of you are already familiar with. This starts with an AV capture session. This needs to get data from somewhere. You create an AV capture device. You add it as the input. Then data needs to go somewhere. In this case, we're using movie file to compress and write the output file. These are all connected with an AV capture connection, and this creates your movie file. So let's convert this into code. And many of you probably have this in your app. First, create an AV capture session. Here we're making a 4K capture session. Then you create the AV capture device, add it as the input. Create your movie file output, and this does the compression and file writing, add it as the output. And then start running and start recording. And then we're capturing. So how do we opt into HEVC? Well, with iOS 10, we added API to check for the available video codecs during capture. And what new with iOS 11 is you can check, does it contain HEVC? On supported devices, it will return true, and you can go ahead and use that in your output settings. And if it doesn't support it, you can go ahead and fall back to another codec like H.264. Now, I want to make an important point here is that order matters with the available video codec types, and for the seed, we made HEVC the first option. So that means if you do nothing else, you will be capturing HEVC content. We really want to get you used to handling this kind of content. Now let's move on to live photos. So we have the same capture graph here, but we use our AV capture photo output, and that makes all the live photos we love and enjoy. So first, let's go over a couple new live photo enhancements we've done in the past year. We now support video stabilization, so no more shaky playback during live photos. We also no longer pause music playback during live photo capture, and we support much smoother live photos, up to 30 frames a second. So let's go over capturing HEVC with live photos. So we have new API in iOS 11 where you can query the available live photo video codec types, see if it contains HEVC, and it will return true on supported devices. Then if it does, go ahead and use it. If not, you can fall back to an existing codec like H.264. I also want to make note that there's the same considerations here, is that order matters with the available video codec types. And for the seed, we made HEVC the first option. So again, if you do nothing else, you will capture HEVC live photos. You might be sensing a pattern here. We really want to get you used to handling this kind of content. Now let's go over the most customizable capture graph, and that's with AV Capture video data output and AV Asset Writer. So you use this if you want to modify the sample buffers in some way. So you might be performing some cool filtering operation. With configuring Asset Writer for HEVC, you have two options. So you can either configure custom output settings where you explicitly specify HEVC, or the video data output can actually recommend those settings for you, and we recommend this API. In iOS 7, we added recommended video settings for Asset Writer. Now, this always recommends H.264. So if you want to stick with that, that's fine. However, in iOS 11, we've added a new API where you can actually pass in the codec type, and we will give you recommended settings for that codec type on supported devices. And with that, let's move on to the export and transcode side of things. So you can transcode to HEVC with AV Foundation and Video Toolbox, and we support MPEG-4 and QuickTime file formats as the destination. And here, API opt-in is required. We support HEVC encode on macOS and iOS. And now let's go over where we support HEVC hardware encode. So we have an 8-bit hardware encoder on our A10 Fusion chip. That's iPhone 7. And we support 8-bit hardware encode on macOS on our 6th generation Intel Core processors. That's the Skylake family, and that's the MacBook Pro with Touch Bar. And on macOS, we have a special 10-bit non-real-time, high-quality software encoder that you can use, and we'll talk about that in a little bit. Now let's start with the highest level export APIs, and that's transcoding with AV asset export session. So with this, you give us an asset, then you pick a preset, and we do all the operations for you, including compression, and then we produce an output movie. So there's no change of behavior for existing presets. If you're using one of the existing dimension-based presets, and it used to give you H.264, it will still do that. We've added new presets here, and those will convert from H.264 or any other codec to HEVC. And these will produce smaller AV assets, up to 40% in some cases, with the same quality. Now let's move one level down the stack to compressing with AV Asset Writer. So AV Asset Writer, you're either generating the sample buffers yourself or getting them from another one of our APIs, like Video Data Output or AV Asset Reader. And AV Asset Writer is responsible for compression and file writing. Again, like I discussed previously, there's two options for AV Asset Writer. You can either explicitly set custom output settings. In this case, we're specifying use HEVC, and you can also specify your bitrate and dimensions. Or you can use one of our convenience settings. In Capture, you can use the video data output. And for general encode, you can use the AV Output Settings Assistant. We've added two new presets here that on supported devices will return HEVC output settings. Now, if you're in the business of creating your own custom output settings, it can be a little tricky. So not all encoders support all output settings. We fixed that problem in iOS 11 and macOS High Sierra, so you can now query the encoder for supported properties to use in your output settings. To do that, you pass in HEVC here, and it will return the encoder ID and the list of supported properties. The encoder ID is a unique identifier for that specific encoder, and with that, the properties and the encoder ID can be specified in the output settings, and you can be sure that it actually works for compression. Now let's move to the lowest level compression interface, and that's compressing samples with VT compression session. So just like with Asset Writer, you might be generating the samples yourself or getting them from another one of our APIs. VT compression session compresses them and produces our compressed media data. So to create a compression session with an HEVC encoder, it's very simple. In this case, we're creating one that's compressing to H.264. Let's go ahead and convert it to HEVC. There we go. Now we're compressing with HEVC with Video Toolbox. So that was pretty easy. Now let's go over a couple considerations on macOS. So for optimal encoding performance on macOS, you want to opt into hardware. This will use hardware when available, and when it's not, fall back to software. So to do that, set the Enable Hardware Accelerated Video Encoder property to true in your encoder specification, and then pass it into VT compression session create. Now, if you're doing real-time encode, you want to often require hardware and never fall back to software. So to do that, you set in your encoder specification require hardware accelerated video encoder to true, and then pass that into your encoder specification. Again, on systems where hardware is supported, this will succeed, but on systems where there's only software encode, this will fail. All right, now let's move on to a couple advanced encoding topics, and the first is bit depth. So if you've ever seen a nice gradient in a user interface or a nice sunrise or sunset, you notice what it looks like in real life versus what it looks like in a movie isn't exactly the same. So you might see these color banding effects in the video version of your movie. And that's because with 8 bits, we don't have enough precision to represent the subtle differences between colors. Now, the great thing about 10-bit is we actually do. So you get these really beautiful gradients. Now, with our macOS software encoder, we actually support 10-bit encode. So first, check that the property is supported. Then if it is, go ahead and use our HEVC main 10 profile for our software encoder. And we want to make sure your entire pipeline is 10-bit. We don't want you going from 8-bit to 10-bit and then back to 8-bit, because that loses precision. So we've added new core video pixel buffer formats to ensure that you can stay in 10-bit. One is listed here. So now for the first time, you can render in 10-bit, encode in 10-bit, decode in 10-bit, and for the first time ever on iOS and macOS, our display pipeline also supports 10-bit. So we get it across everything. Now let's go over our second advanced topic, and then it's hierarchical encoding. So to understand a little bit about this, we need to go over a little bit of video encoding 101. There's 3 major frame types in compressed video, and the first is an iframe. You can think of iframes like an image file, and they can be decoded independently. Then we have a p-frame, and p-frames refer to previous frames. So think of them like a one-way diff, and they only contain information that isn't in the previous frame. Now we have their cousin, the b-frame. B-frames refer to previous and future frames, and they're like a fancy multi-directional diff. So they only contain information that isn't in either frame they're referencing. Now let's pretend we have a decoder that can only handle 30 frames a second. And let's say we have content that is 240 frames a second. Well, that means we need to drop some frames before we can decode because it can't keep up. So when can we drop frames? We can drop frames when another frame doesn't depend on it. So in this case, we can drop the last p frame because it refers to another frame, but no frames refer to it. So let's go ahead and drop it. We can also drop the b frame because it refers to other frames, but no frames refer to it. So let's go ahead and drop it. Now let's move to a real-world case of encoding 240 frames per second content. So this is a typical encoding scheme used when creating content compatible with low-end devices. So for example, when encoding 240 frames a second content, we'll have 1 non-droppable frame for every 7 droppable. So this gives us a lot of flexibility during playback. On devices that support 120 frames per second decode, we can handle that. On devices that only support 30, we can also play back there. Now let's throw in our frame references. Because these frames are droppable, they can't refer to each other, and they all refer to the non-droppable frame. Now, those of you with compression experience are already seeing one problem, is that compression suffers because we can't refer to the nearby frames. So they're all referring to the non-droppable frame, and a lot might have changed between the non-droppable and the droppable frame. All right, so that's problem number 1 that we're going to fix. Now let's step through and decode down to 30 frames a second. So first, let's say we can't handle 240 frames a second. Let's go ahead and drop some frames. So here we're dropping down to 240 frames a second, and let's say we still can't keep up. We need to go down to 60 frames a second. Let's say we have our decoder that can only handle 30 frames a second, and we can't even handle 60 frames a second. So we go ahead and drop this last frame. Now, I was really guessing about what frames to drop. So there's no indication at all about whether I should drop every other frame, or just the first half, or just the second half. So let's fix this problem too. We can fix that with a concept known as temporal levels. And this allows us to organize frames about which ones to drop first. So let's go ahead and re-encode our content. And you can already see that this is way more organized. So first, we drop temporal level 3, and then 2, and then 1, and there's no guessing involved. So this really helps. Now let's throw in our frame references. And you can already see there's a big difference here, is that the reference frames are much closer together, and they're often referring to frames that are just before or just afterwards. So this really improves compression. Now let's go through, and let's say we have our same decoder that can only handle 30 frames a second. We need to drop some frames. Well, there's no guessing involved. We drop temporal level 3. Now we're down to 120 frames a second. Let's drop down to level 1. Now we're down to 60. And now we have a level that our decoder can actually handle. So this reduces guessing with frame dropping. Let's go over what we've learned. So with HEVC hierarchical encoding, we have improved temporal scalability. There's a much more obvious frame dropping pattern, and it removes frame drop guessing during playback. We also have improved motion compensation. The reference frames are much closer to each other, so we can reuse more parts of other frames, and it also improves compression. We're also using file annotations, and for those of you that like to read specs, check out MPEG 4 Part 15, Section 8.4. And basically, we're using sample groups so no bitstream is parsing. No, sorry. We're using sample groups so no bitstream parsing is necessary to get at this information. So that really helps. All right, how do we opt into this? So you want to opt into this if you want to create compatible high frame rate content. And there's 2 properties you should set. You set the base layer and the capture frame rate. First, check that they're supported on the encoder you're using, and then set the base layer frame rate. This is the temporal level 0 frame rate. In our previous example, this was 30 frames a second, and then set the expected frame rate. In our previous example, this was 240 frames a second. The base layer must be decoded, and we can decode or drop other levels. So now that you're all experts in hierarchical encoding, let's move it over to Brad for the image side of things. Thank you.
Thanks, Eric. I'm Brad Ford from the camera software team, and I get to talk to you about the other 4-letter acronym that begins with HE. Here's the agenda for the rest of the session. First, we're going to cover what is heif at a high level. We'll start at the very lowest level when we talk about reading and writing files with heif. Then we'll go up to the top of the stack and talk about how to use general use cases and common scenarios with heif. And we'll end with the topic that's most near and dear to me, which is capturing heif. So first off, what is heif? Heif is the high-efficiency image file format. The second F is implied and silent. You don't need to call it heif. You'll just embarrass yourself in front of your compressionist friends if you do that. It's a modern container format for still images and image sequences. It's part of the MPEG-H Part 12 specification, and by way of curiosity, it was proposed in 2013, and it was ratified in summer of 2015, just 1.5 years later. If any of you know anything about standards organizations, 1.5 years is kind of like 2 days in real people time, so you know it must be an awesome spec. The technical detail I'm sure you're most interested in, and the reason that you came today, is how to pronounce it. So I used the scientific method. I polled all the engineers on my floor, and the voting was largely along party lines. The German speakers said heif, and the French said F, and the Russian said heif, and heif was the runaway winner, though. That's heif, as in I can't believe how big or how small the files are. Now, my Finnish office mate is quick to point out that Nokia researchers were the ones that came up with the spec, so the Finnish pronunciation should win. That would be the 1% heif. Well, as for me and my floor, we're going to call it heif. It can use HEVC intra-encoding, which unsurprisingly compresses much better than the 20-year-old JPEG. 2 times as well, as a matter of fact. That's an average of 2 times smaller, not up to 2 times smaller. We used qualitative analysis on a large data set of images to arrive at this number, ensuring visually equal quality to JPEG. It supports chopping up an image and compressing it in individual tiles. This allows for more efficient decompression of large images in sections. heif also has first-class support for auxiliary images, such as alpha, disparity, or depth maps. Here's a grayscale visualization of the depth map that's embedded in this heif file. Having depth information opens up a world of possibilities for image editing, such as applying different effects to the background and foreground, like this. Here I've applied the noir black and white filter to the background and the fade filter to the foreground. So notice that the little girl's tights are still in pink while everything behind is in noir. Noting the gradations of depth, I can even move the switchover point of the filters like this. Keep an eye on her flower. Now just her hand and the flower are in color while everything else is black and white. You can even control foreground and background lighting separately, exposure such as this. Now she looks like you photoshopped her into her very own photo. I'm not saying you should do it, I'm saying you could do it. That was just a teaser for a 2-part session that we had on depth, and that's sessions 507 and 508. I hope you'll make some time to look at those videos. When it comes to metadata, heif has a great compatibility story. It supports industry standards EXIF and XMP as first-class citizens. heif isn't just for single images, it also supports image sequences such as bursts, exposure brackets, focus stacks. It also has affordances for mixed media, such as audio and video tracks. Let's do a demo, shall we? Okay, and this is a showcase that takes place in Apple's very own Photos app. All right, I'm going to start with Pano, and this is a nice-looking Pano. This one is from Pothole Dome in Yosemite. It looks great. It's sort of what you would expect from a Pano until you start zooming in. So let's do that. Zoom in a bit. Looks nice. Let's zoom in a little more, and then zoom in a little more, and zoom in a little more, and keep zooming, and keep zooming. Oh my gosh, I can see what the speed limit is. And wow. There are cars there, and there are porta potties. I can even go and take a look at the peaks in the background. Notice how it snaps into clarity as I go. This is actually a 2.9 gigapixel pano. It's 91,000 pixels by about 32,000 pixels. The RGB TIFF file for this is well over 2 gigabytes, and I assure you it brings any fast Mac to its knees. Whereas the heif file is just 160 megabytes. You literally cannot do this with JPEG, since JPEG maxes out at 64K by 64K pixels. Heif does not max out. It supports arbitrarily large files, and it keeps the memory in check by efficiently loading and unloading tiles. So while I have this enormous data set in front of me, I'm never using more than 70 megabytes of memory at a time in the Photos app. So it's responsive, and I can zoom in and zoom out. I could do this all day long, but I should probably go back to slides. On all iOS 11 and Mac OS 10.13 supported hardware, we read and decode 3 different flavors of heif. The 3 different extensions you see here relate to how the main image in the file is encoded. For heik.heic, also the UTI of public.heic, that refers to heif files in which the main image is compressed with HEVC. The second flavor is avci, in which the main image is compressed with H.264. And then the .heif extension is reserved for anything else. It could be JPEG inside, it could be any of the supported codecs. We only support one form of heif for encode and writing, and that's the heic format. In other words, the one in which you use HEVC. We figure if you've gone far enough to adopt the new file container, you might as well adopt the greatest compression standard as well. Support is currently limited to iOS 11 devices with the A10 Fusion chip. All right, let's go over to low-level access to heif. The lowest level interface on our platform for reading and writing images is Image.io. It encapsulates reading from either a file or in-memory data source using an object called CG image source. It also supports writing to files or to immutable data using CG image destination. These objects have been around for a long time. You've probably used them. To open a JPEG image file on disk, this is how you would do it using Image.io. First, you create the URL. Then you call CG image source create with URL to create your source. The last argument is an options dictionary where you can optionally pass the UTI of the input. It's not needed when you're opening a file on disk because the UTI can be inferred from the file path extension. Once you've got a CG image source, you can do several things with it, such as copy the properties at any index. That's getting metadata out of it, such as exif. You can also create a CG image from any of the images in the file. For JPEG, there's typically only one image in the file. CG image is, of course, like a promise, a rendering promise. The JPEG data can be lazily decoded when necessary using CG image, such as when you're rendering it to a CG bitmap context. You can also get a thumbnail image using a variety of options. For instance, the maximum size that you would like, what to do if there's none available in the file. And when you call CG image source create thumbnail at index, it does decode right away. Now, here's the analogous code for opening a .heic file. Can anyone spot the differences? Here, I'll make it easy for you. That's it. It's a comment and it's a file path. That's it. In other words, CG image source just works. The one difference you don't see is how the HEVC is being decoded. On recent iOS devices and Macs, the decode is hardware accelerated, whereas on older devices, it's done in software and will thus be slower. A quick word on the tiling support that we just saw in the demo. CG image source can provide a dictionary of properties about the image by calling CG image source copy properties at index. And the properties dictionary is a synonym for metadata, exif, Apple MakerNote, etc. There's also a subdictionary called the TIFF subdictionary, in which you'll find the size of the encoded tiles as the tile length and tile width. By default, they are encoded as 512 by 512 pixels. CG image source provides you with CG images, as we saw, and CG image has a nifty method called cropping to that takes advantage of the tiling. This call creates a new CG image containing just a subsection of another image. This isn't a new API, but it works really well with heif, where the tiles are encoded individually. You don't need to worry about the underlying encoded tile size. You can simply ask for the subregion that you want to display or render, and know that under the hood you're getting all of that tiley goodness. It's only decoding the tiles that are necessary for that subregion. Now let's talk about the writing side. Here's how you write a JPEG with ImageIO. You, after creating a CG image destination, calling CG image destination create with URL, where I should point out you do need to specify what the UTI is. Here I'm using avfiletype.jpg, which is the same as the UT type public.jpg. I'm being careful with the result. I'm using guardlet just in case destination is nil. Now, with the current JPEG, the only reason it would be nil is if you ask to write to a file that's outside your sandbox. But to be defensive, you should really write code in this manner. Next, you add your CG image or images one at a time with accompanying metadata if you would like. And then when you're done, you call CG image destination finalize, which closes the container for editing and then writes it to disk. Now let's look at the heif writing. Again, differences are very small. Just the file path extension, the UTI, the comment. One important difference here, though, between JPEG and heif is that creating a CG image destination will fail on devices with no HEVC hardware encoder. And when it fails, destination is nil. So the good defensive code that I wrote on the previous slide is even more important to do with HEVC, where there's now a new reason that the destination might be nil. Please always make sure that you check. This is the one and only way to know whether writing to heif is supported on your current platform. Also worth noting is that ImageIO has added support for reading and writing depth maps, as I talked about earlier. We've done that for both heif, and we manipulated JPEG in strange sorcery ways that we probably shouldn't talk about. I'm not going to delve deeply into that, though, because it's covered in the dedicated session 507 and 508, where we talk about depth. And I hope you'll go look at those sessions, because there are many segues to the auxiliary image format in heif. All right, it's time to move on to our next major topic, which is high-level access to heif. But before we do that, I feel that WWDC should be a cultural experience, culturally enriching, not just an educational one. And that's why I want you to rest your brains for a moment with some compression poetry. All right, wait for it. JPEG is yay big, but heif is brief. Thank you. See, it's compression poetry, so it's small. Did you like that? Do you want to hear some more? OK, let's do another one. Here's a compression haiku. HEVC has twice as many syllables as JPEG. Progress. Thank you. All right, let's move on. I'm sure they'll edit that out later. OK, we're going to talk about heif and PhotoKit. PhotoKit is actually two frameworks. It's Photos Framework and Photos UI. And it's very high level. It sits even above UIKit. The way that you work with heif and PhotoKit when applying adjustments, we're going to cover just briefly. And we're going to talk about how you apply adjustments in 3 different scenarios: photos, videos, and live photos. And then we'll talk about common workflows that you would use with PH Photo Library. Let's briefly outline the steps involved in applying an edit or an adjustment to an asset using Photo Library. You ask the PH Photo Library to perform changes, and in that change request, you start with a PH asset that you want to edit, such as a photo, and you call request content editing input on the asset to get a PH content editing input. This is the guy that gives you access to all the media associated with your asset, such as a UI image, a URL, an AV asset, or a live photo. Next, you create a PH content editing output by calling init with content editing input. The editing output tells you where to place all of your rendered files on disk by providing you with a rendered content URL. You then perform your edits to the media that's provided you from the editing input, and then you write them to the specified location. Finally, the PH Photo Library validates your changes and accepts them as a whole or rejects the change. So the rules with respect to rendered output images are unchanged, but you may not have been aware that they were in force. In iOS 10, your output images must be rendered as JPEG with an EXIF orientation of 1. That is, if there is any rotation to be done, it is baked into the image in the output rendered file. You may have overlooked this detail since probably 99% of the content that you were editing was provided as JPEG, and then you just outputted it to the same format. But now you will see a proliferation of input content that is heif. So you should be well aware that you must still render all of your output content to JPEG with EXIF orientation 1. Here's the code for it. First you make a CI image. This would be one way of doing it. You could make a CI image from the content editing inputs file URL, and then apply your edits. Here I'm doing both application of a filter and baking in the orientation. And then when I'm done, I call CI context handy dandy write JPEG representation, which if you've used this boilerplate code in the past, it still works correctly because it's outputting to a JPEG regardless of what the input was. Our second applying adjustments use case relates to videos, and the rule, again, same as iOS 10, is that no matter what the format of your input movie content, you must produce a movie compressed with H.264 as your output. Yes, even if the source movie is HEVC, you still need to render to H.264 for output. Here's some boilerplate code to edit video content that looks like this. First, you get an AV asset from the PH content editing input. Then you can create an AV video composition in which you are handed each frame one at a time, and you can get them as CI images and then request an object that has a mouthful of a name, AV asynchronous core image filtering request. You get a CI image, and then you produce a CI image. When you're done rendering it, you call request.finish. And then as a final step, you export your AV asset to a file on disk at the URL told to you by the PH content editing output. Now here's the important part. The preset to use is AV asset export preset highest quality, or any of the existing ones, as Eric said, still compressed to H.264. Don't use the similarly named new ones which have HEVC in the name, because your change request will fail with an error. Finally, applying adjustments using live photos, the video content of live photos. What I'm talking about here is the moving aspect of a picture when you either swipe between photos that were live photos or when you force touch on a picture or swipe between pictures. This is the simplest use case, as you never get to deal directly with the input or output files. You're passed CI images, and you produce CI images. The encoding is done on your behalf. There's a lot of good code to look at here, but I'm not going to spend a lot of time on it. You can pause the video later and take a good long look at it. The one take-home point is that after you've filtered each frame in a live photo movie, you can tell the live photo content to save your live photo to a given URL, and that's it. The live photos will be saved out using H.264 on your behalf, just as the stills will be encoded as JPEG. Okay, let's move over to the common workflows with PhotoKit. When displaying content from your photo library, you use an object called the PH Image Manager. And this provides you with one of three things. You could get a UI image if it's an image, a player item if it's a video, or a PH live photo if it's live photo content. Here you don't need to make any changes because all of these are high-level abstractions in which you don't care where the sources came from. All you're doing is displaying them. No code changes needed here. The next is backup. When using PhotoKit for backup purposes, you probably want to access the raw assets, such as the heif files in the QuickTime movies, and you do that using PH Asset Resource Manager. It will give them to you in the native format. The only thing to be aware of here is that you might get different file types coming than you're used to, so make sure that you're ready for it. The third and most complicated case is sharing. Here you're sort of leaving Apple's nice walled garden. You have to think about your compatibility requirements. Are native assets okay? You might be doing your clients a favor, or you might be doing them a disservice by giving them heif content, depending on whether they're ready for it. So here you must weigh compatibility versus the features that heif affords. If you do choose compatibility over features, you can ensure format compatibility by specifying the output format explicitly. For images, you can just check the UT type that you get and see that it conforms to, say, JPEG, and if it doesn't, explicitly convert it. With videos, you can always force compatibility by requesting an export session with a preset that you know will deliver H.264, such as preset highest quality. All right, on to our last topic of the day, capturing heif. Finally, one that I know what I'm talking about. But let's do compression haiku number 2. Please, would you let me? It's fun for me. Here we go. Heif, a container, compresses 4 times better than HEVC. Think about that. Okay, so why are we wasting our lives saying HEVC? It's supposed to be a good codec, right? Why aren't we calling it hevc? All right. So Eric mentioned that AV Capture photo output added support for live photo movies encoded with HEVC. This class was introduced last year as the successor to AV Capture still image output. It excels at handling complex still image capture requests where you need multiple assets delivered over time. It is currently the only way on our platform to capture live photos, Bayer raw images, Apple P3 wide color images, and new in iOS 11, it is the only interface on our platform for capturing heif content. Heif capture is supported on the A10 chip devices, which are iPhone 7 Plus, iPhone 7, and the newly announced iPad Pros. We'll do a brief refresher on how to request and receive images with the photo output. First, you fill out an object called an AV Capture Photo Settings. This is sort of like a request object, where you specify the features that you want in your photo capture. Here it's the orange box. Here I've indicated that I want auto flash, meaning photo output only use the flash if it's necessary, only if the light is low enough to warrant it. I've also asked for a preview-sized image to accompany the full-sized image so that I can have a quick preview to put on screen. I don't know exactly what the final aspect ratio of it will be, so I just ask for a box that's 1440 by 1440. I then pass this settings object along with a delegate that I provide to the photo output to start or kick off a capture request. Now, the arrow on top shows when the request was made. And now I'm sort of tracking this package delivery. Photo output calls my delegate back with one method call at a time. Very soon after I make the request, the photo output calls the delegate's first callback, which is will begin capture for resolved settings. And it passes you this blue box, which is a resolved photo settings. This is sort of like the courtesy email that you get saying, we've received your order, here's what we'll be sending you. And this resolved photo settings sort of clears up any ambiguity that you had in your settings that you provided at the beginning. In this case, we can now see that flash is not auto, it's true or false. So it's become true. We know that the flash is going to fire. Also, we now know what the final preview image resolution is going to be. Finally, after we get the will begin capture for, our second callback that we receive is will capture photo for resolved settings. This is delivered coincident with the shutter sound being played. And then shortly thereafter comes did capture photo for resolved settings, just after the image has been fully exposed and read out. Then some time typically passes while the image or images are processed, applying all the features that you asked for. When the photo is ready, you receive the did finish processing photo sample buffer callback, and the image or images are delivered to you. Here I got the main image and the preview image. They're delivered together in the same callback. Finally, you always, always, always get the did finish capture for resolved settings callback, and that is guaranteed to be delivered last. It's the photo output's way of saying, we're done with this transaction, pleasure doing business with you, you can clean up your delegate now. This programming model has proved to be very flexible. We've had a lot of success with it because we've been able to add new methods to the delegate as needed when we add new features. For instance, we added support for raw images. There's a callback for that. We added support for live photos. There's a separate callback for that, for getting the movie. So it would seem like heif would be an easy addition to this very flexible programming paradigm. Unfortunately, it's not. The incompatibility lies in the core media sample buffer, which is and has been the coin of the realm in AV Foundation for many, many years. We have used it for delivering still images since iOS 4. It's a thin container for media data such as video samples, audio samples, text, closed captions. heif, on the other hand, is a file format, not a media format. It can hold many media types. Also, CM sample buffers can, of course, carry HEVC compressed video, but that HEVC compressed video doesn't look like the heif containerized HEVC. Remember, heif likes to chop things up into individual tiles for quick decode. You can't store that kind of HEVC compression in a frame in a QuickTime movie. It will just confuse the decoder. So at this point, you might be asking yourself, if we have this fundamental tension between file container and media container, how were we able to use CM sample buffer for so many years with our photo output and still image output? Well, the answer is JPEG. We got away with this because of the happy coincidence that JPEG, the image codec, and JFIF, the file format, are virtually indistinguishable from one another. Both are acceptable as images in another container, such as a QuickTime movie. So the answer to our quandary is to come up with a new, purpose-built, in-memory wrapper for image results, and we call that the AV Capture Photo. It's our drop-in replacement for CM sample buffer. It is, in fact, faster than CM sample buffer because we are able to optimize delivery of it across the process boundary from the media server, so you get even better performance than you did in iOS 10. It's 100% immutable, unlike the CM sample buffer, so that it's easier to share between code modules. It's also backed by containerized data. I'm going to talk more about that in a minute. Let's talk about some of its attributes. It has access to critical information about the photo, such as the time at which it was captured, whether or not it's a Bay or RAW photo. And for uncompressed or RAW photos, you get access to the pixel buffer data. Also, sideband information travels with the AV Capture Photo too, such as the second, smaller preview image that you can ask for. You can also now request a third image that's even smaller to be embedded as a thumbnail in the container. An image I/O property style metadata dictionary is provided that can contain EXIF or other metadata that you've come to expect. And with the iPhone 7 Plus dual camera, you can request that a depth data map be delivered with the AV Capture Photo results as well. AV Capture Photo also provides a number of convenience accessors, such as a reference to the resolved settings object that we saw in previous slides. Also, it gives you easy access to bookkeeping about the photos. For instance, if you've fired off a request for a RAW plus HEIC, you would expect to get 2 photos. So the photo count accessor will tell you, is this photo 1 or photo 2? If this photo is part of a bracketed capture, such as an auto exposure bracket of 3 or 4 different EV values, it can tell you which bracket settings were applied to this particular result, as well as its sequence number, and whether lens stabilization was engaged. AV Capture Photo also supports conversions to different formats, so it's friendly and able to move to other frameworks that you would use with image processing. First and foremost, it supports conversions to data representations if you just want to write to file, and it can produce a CG image of either the full-size preview the full-size photo or the preview photo. Now, the mechanism for opting in to get an AV Capture Photo instead of a CM sample buffer is just that you need to implement one new delegate method in your AV Capture Photo Capture delegate, and that's this one here. It's very simple. It just has 3 parameters. It gives you the AV Capture Photo and optionally an error. Now, error or not, you always get an AV Capture Photo with as much information about it as possible, even if there's no backing pixel data. The following 2 really lengthy delegate methods have been deprecated to help steer you towards the new and better. We used to have separate callbacks for getting the raw or the uncompressed or compressed, did finish processing photo, which would give you a CM sample buffer, or did finish processing raw photo, which would give you a sample buffer. You needn't use these anymore. You can just use the new single, which subsumes both of them into one. All right, in iOS 10, we supported the following formats. For compression, all you could get was JPEG. For uncompressed, you had your choice of 2 flavors of 420 or BGRA, and of course we supported Bayer RAW. Now in iOS 11, in addition to adding HEVC support, we're adding a new dimension to this as well. Every image format that you request is also backed by a file container format. In other words, implicitly, every image that you capture is being containerized. For HEVC, the implicit container is HEIC. For JPEG, it's JFIF. For the uncompressed formats, it's TIFF. And for raw formats, as before, it's DNG. Now, why would file containerization be a good thing? The answer is performance. Let me explain using a case study. So here's the old way you would get a JPEG and write it to disk. Photo output would deliver you a sample buffer with a full-sized image and a preview image, and it would attach some metadata to it, such as EXIF. If you wanted to mutate that in any way, you would have to wait until it delivered the callback, and then you would get the attachment that had the EXIF, manipulate it, and re-add it to the sample buffer. Then when it came time for writing it to disk, you would call photo outputs JPEG data, photo data representation, and pass it the 2 buffers. Out comes a JPEG data ready to write to disk. While in code it looks simple, a lot is happening under the hood. Because we conflated preview image with embedded thumbnail image, we had to take something that was sized for the screen and scale it down, compress it to JPEG, incorporate all of your EXIF changes, and rewrite the full-size image. So a lot of scaling and compression done just because you wanted to include a thumbnail with your image and manipulate a little bit of metadata. Not efficient at all. Now in the new way, AV Capture Photo lets you specify up front what you want in the container. If it has enough information to prepare the file container right the first time, then it's done before you ever get the first callback. The way you do this is you fill out some extra features in the AV Capture Photo settings. This time you can specify in advance the codec that you want and optionally the file type. You specify metadata that you would like to add, such as GPS location. You can now do this before you've even issued the request. You can also tell it, I would like an embedded thumbnail, and I would like it using these dimensions. You then submit your request to the AV Capture Photo output, and eventually it gives your delegate an AV Capture Photo as its result. This AV Capture Photo is backed by something that's already in a HEIC container. It's already been compressed in tiles. It's already embedded that thumbnail image that you asked it to. It's already put the metadata in the correct place. So the final call that you would do to write it to disk, photo.filedataRepresentation, is much simpler than in the previous example. All it's doing is a simple byte copy to an NSData of the backing store. No additional compression or scaling or anything. It's all done in advance. This is much more efficient, and especially when we're dealing with heif, it's necessary to get all of the performance out of that great tiling format that I talked about earlier. Now let's switch over to a few performance considerations with HEVC and heif. The first is what to do about photos that are taken during still capture. When you take a HEIC photo while capturing a movie, you should be aware that the same hardware block that's compressing video, that is the one that does H.264 or HEVC compression, is also being asked to do double duty if you want to encode a HEIC file where HEVC is the compression format. That hardware block may be very busy indeed if you are capturing high bandwidth video, such as 4K 30 or 1080p 60. Video is on a real-time deadline, so it gets priority over stills. This means that it may take longer to get your still results back, And it also may mean that they are up to 20% larger than they would be otherwise because the encoder is too busy to use all of the features that it would if it didn't have to meet that real-time deadline for 30 or 60 frames a second. So our recommendation is if you're capturing video and taking stills at the same time, you should use JPEG for the photos to leave the encoder for HEVC as available as possible for the video. Another concern is HEVC and heif bursts. This is where you mash on the button and you're trying to get a constant frame rate, maybe 10 frames a second of captured images. HEVC encode obviously is doing a lot more work than JPEG did. It's delivering a file that's half the size of JPEG. Therefore, HEVC encode does take longer. Now, we've benchmarked, and we're comfortable that HEVC heif can meet the 10 FIPS minimum requirement for bursts. But if you need to capture at a higher frame rate than that, our recommendation is to go back to JPEG for bursts. And we've heard a lot about compression today, and I feel I would be remiss if I didn't give you my thoughts on WWDC. It is, after all, a compression talk. So I can't just leave this dangling there. Worldwide Developer Conference, 9 syllables. WWDC, 8 syllables. That is like the worst compression format ever. It's lossy. It's like 0.1 to 1 compression ratio, which is even worse than lossless JPEG. So please, as a service to me, for the rest of the conference, would you please only refer to the conference as dub, or I'll also accept woduk. All right, let's summarize what we learned today. HEVC movies are up to 40% smaller for general content than H.264, and for camera content on iOS, they are 2x smaller. Also, HEVC playback is supported everywhere on iOS 11 and High Sierra, sometimes with software, sometimes with hardware. And to create HEVC content, you need to opt in to new capture APIs or export APIs. Also, we learned about HEIC files, that they are twice as small as JPEGs, and that decode is supported everywhere on iOS 11 and macOS, where capture is supported on iOS only, and where we have an A10 chip, and you do that using the new AV Capture Photo interface. For more information, here is the URL for today's session. I also wanted to point you to some sister sessions to this one. The first one in the list, high efficiency image file format, is one that went straight to video. This is where we really delve deeply into the bits in the heif file. It's a great presentation. You should definitely listen to it. It's performed by Davide, so you get the nice Italian accent going at the same time. Also, the Introducing heif and HEVC, which was on Tuesday, which gave a higher level introduction to what we talked about today. And finally, the depth sessions that I've made several references to. They have several segues to the auxiliary image format that we use to store depth in heif. Thank you, and enjoy the rest of the show.